Hello everyone, my name is Ming Fu. I'm a PhD student from Huazhong University of Science and Technology. Today, my talk is about the design trade-offs for data duplication performance in backup workloads. This is a joint work with the researchers listed here. Today, we are living in big data era. IDC reported we have 4.4 gigabytes of digital data in 2013. And expectedly, we will have 44 gigabytes of data in 2020. And moreover, many researchers from industry and academic have reported the wide existence of data redundancy in real-world applications. So we can use compression technologies to improve the storage efficiency. And the data duplication is a scalable compression technology, different from traditional compression technologies such as gzip. Data duplication is faster due to its coarse-grained compression, and because it is faster and more scalable, it is able to look for duplicated chunks in a larger scope for higher compression ratio. And this figure illustrates a typical duplication system. The backup stream will be first divided into the trunk engine will divide the backup stream into non-overlapping chunks, and then the hash engine will calculate the fingerprint for each chunk. Then we check the fingerprints in DRAM fingerprint cache. If we find a match, it's a duplicated chunk. Otherwise, we further check it in the key value store. And if we find a match, it is a duplicated chunk. Otherwise, it's a unique chunk. For each duplicated chunk, we only need to write a fingerprint to the recipe, and for a unique chunk, we need to write the chunk to the container store, insert the fingerprint into the key value store, and write the fingerprint to a recipe. In order to design an efficient duplication system, we have a lot of challenges to be addressed, including chunking, indexing, defragmenting, restoring, garbage collecting. And as a result, we have a huge number of papers, solutions, and design choices, and we got a huge, extremely huge parameter space. In practice, it is very difficult to determine which one is better, and better in what metric, and moreover, how about their interplace. So in this paper, we will first propose a taxonomy to help researchers to understand the parameter space in deduplication system, and then we design and implement a general purpose deduplication framework for evaluation. And finally, we present our experimental results and draw conclusions. In this paper, we mainly explore the fingerprint index, the rewriting algorithm, the restore algorithm, and their interplace. And the table lists the major parameters we discuss, including the key value mapping, the fingerprint cache, the sampling, segmenting, segment selection, segment prefetching, defragmenting, and restoring. However, due to the time limit, I cannot go through all these parameters in this talk. You can find more details in the paper. A duplication system requires a huge key value store to identify duplicates. However, an in-memory key value store is not cost efficient. We built a financial cost model in our paper using the unit prices from Amazon. We found if we keep the key value store in DRAM, more than 50% of the storage cost is for DRAM. So alternatively, we can keep the key value store on disks. However, it easily becomes the performance bottleneck compared to the fast container-defined chunking algorithm. So modern fingerprint indexes explore the workloads characteristics of backup systems to prefetch and cache fingerprints. Hence, a modern fingerprint index consists of two major components, a key value store and a fingerprint prefetching and caching module. Based on the two components, we propose a taxonomy for fingerprint index. Based on the use of key value store, we have exact duplication and near exact duplication. In exact duplication, we index all fingerprints in the system in the key value store, and we try to eliminate all duplicated chunks. The near exact duplication uses some sampling methods to partially index the fingerprints to reduce the size of the key-value store. Based on the prefetching policy, we have logical locality and a physical locality. The logical locality is the trunk sequence before deduplication, which is preserved in recipes. And the physical locality is the physical layout of stored trunks, which can be considered as the fingerprint sequence after deduplication, which is preserved in containers. Let's first compare the exact deduplication and the near exact deduplication. Exact deduplication indexes all stored fingerprints, so its index is extremely huge. We generally need to keep the key-value store on disks for storage savings, for cost savings. So the fingerprint prefetching and caching is very important to improve backup throughput. The near exact deduplication indexes only sampled fingerprints, so its key-value store is very small, and we can keep it in the DRAM. The fingerprint prefetching is very important to improve the deduplication ratio. In summary, near exact deduplication trades deduplication ratio for higher backup and restore performance and a lower memory footprint. From the aspect of financial cost, whether a lower memory footprint indicates a lower financial cost, we found it is not true because based on our cost model, near exact deduplication needs to achieve 97% of deduplication ratio in exact deduplication. And based on our experimental results, it is extremely difficult to exploit physical locality. The key-value store maps the fingerprint to its physical location, namely a container ID. This figure illustrates the workflow. For each input fingerprint, we first check it in the fingerprint cache. If we don't find a match, we further check it in the key-value store. And if we find a match, we know which container the trunk locates. So we can prefetch all fingerprints in the container into the fingerprint cache. The weakness of this approach is that the prefetching efficiency decreases over time due to the fragmentation problem. For example, older containers will have many useless fingerprints for new backups. It indicates the backup throughput will decreases over time in this kind of system. For near exact deduplication, a problem is how to select representative fingerprints in each container. Generally, we have two basic approaches. The first is to select the fingerprints that mode R is 0 in a container, or we can select the first fingerprint every R fingerprints in a container. The R is the sampling ratio. Based on our observations, the second sampling method achieves significantly better deduplication ratio than the first method. To explore its logical locality, the key-value store maps the fingerprints into its logical location, namely a segment in a recipe. In this case, the recipe is divided into non-overlapping segments, and the segment serves as the prefetching unit. The workflow is slightly different from the physical locality. When we find a match in the key-value store, we load the recipe. We load a segment in a recipe into the fingerprint cache. The advantage is we have no fragmentation problem in this approach. However, its weakness is we have an extremely high update overhead to the key-value store. It is because not only unique fingerprints, but also the duplicate fingerprints will have logical locations in new recipes and new segments. One possible optimization is to only update sample duplicate fingerprints to reduce the update overhead. Two major problems is how to segment and sampling. In the paper we examine the different segmenting algorithms and sampling algorithms, and we also observe a performance problem of this approach in some data sets where self-references are very common, such as our virtual machine data set. So in this kind of data set, we recommend to explore with a more complicated workflow than this simple workflow shown in the figure, namely the similarity detection approach. Actually, in logical locality, we have a lot of parameters and design choices, including the segmenting, sampling, segment selection, segment prefetching, and key value mapping. And the table summarizes existing work. And we have a detailed discussion in the paper about the design choices and their combinations. And the rewriting algorithm is an emerging dimension in deduplication system to reduce the fragmentation. The fragmentation is an intrinsic problem in deduplication system. It can be considered as the deviation between the logical locality and the physical locality. It will hurt the read performance. So in an ageless deduplication system, its restore performance is very poor. And this figure shows the how rewriting algorithms work. Rewriting algorithm tries to find a fragmented chunk during backup. And if we identify a chunk as fragmented, we will rewrite it into a new physical location rather than duplicating it. We currently have some rewriting algorithms in two kinds of rewriting algorithms: the buffer-based algorithm and the history-aware algorithm. The buffer-based algorithm uses a rewriting buffer to hold consecutive backup, consecutive chunks, and identify fragmented chunks in the scope of the buffer. And the history-aware algorithm explores historical information to identify fragmented chunks. Their basic observation is the consecutive backup stream are very similar. So a fragmented chunk in this backup remains fragmented in the next backup. So, however, all of this previous work on rewriting algorithms assume a simple fingerprint index without considering the fingerprint prefetching. So how about their interplays with the state-of-the-art fingerprint indexes? We are mainly concerned about two questions. The first is how does the rewriting algorithm improve the fingerprint index exploit in physical locality? And the second is how do the different prefetching schemes affect the efficiency of the rewriting algorithm? We will answer these two questions later. The restore algorithm is to reconstruct a backup stream efficiently, while the rewriting algorithm determines the trunk layout, determines how to write, and the restore algorithm determines how to read. An efficient restore algorithm will improve the restore performance under limited memory. Existing restore algorithms, including the traditional aerial cache, the Baladis optimal replacement cache, and the rolling forward assembly area. So, we will examine their interplays with the rewriting algorithm. We have briefly discussed the parameter space. However, as far as we know, none of the existing platforms can evaluate the entire parameter space. So we develop a general purpose framework for evaluation. This figure illustrates the architecture of our framework, including a fingerprint index, container store, and the recipe store. It also shows the backup pipeline, including trunk phase, hash phase, dedupe phase, rewrite phase, filter phase, and append phase. The trunk phase will divide the stream into chunks. The hash phase will calculate fingerprints. And the dedupe phase will check will examine the duplicates in the backup stream. The rewrite phase will identify fragmented duplicate chunks. The filter phase determines whether we need to write the trunk according to the flags marked by the previous two phases. We separate the dedupe phase, rewrite phase, and filter phase for modularity, so we can implement a new rewriting algorithms in the rewrite phase without the need of modifying the fingerprint index and vice versa. This is the restore pipeline. The first phase, read the recipe phase, reads the recipe and open and reads the recipe for recovery and feeds the fingerprint sequence with the next phase. The second phase, restore algorithm phase, will receive the fingerprints and fetch chunks from the container store. And it will feed the trunk sequence to the next phase. We can implement different restore algorithms in this phase. In the last phase, we will reconstruct the fires using the received trunk sequence. And regarding the garbage collection problem, users can set a retention time for the backups. So all expired backups will be deleted automatically by D-frame. And then how to reclaim the invalid trunks becomes a major challenge. We develop some algorithms to accelerate the garbage collection, and more details can be found in our ATC paper. And using the D-frame framework, we can evaluate the parameter space to find existing solutions and potential solutions can be considered as a point in the space. We can evaluate each point in the space to find which one is better and better in what metrics. And we use 3 data sets for evaluation, including kernel, VMDK, and RDB. Kernel consists of 258 versions of Linux kernel source code, and the VMDK consists of 127 consecutive snapshots of virtual machine disk imaging, and the RDB consists of 212 consecutive snapshots of a Redis database. The RDB dataset is very different from the other two datasets because the self-references is very common in this dataset, and the results in this dataset is very different from the other two datasets. We use the following quantitative metrics for evaluation, including deduplication ratio and memory footprint, storage cost, lookup and update requests to key-value store per gigabyte, and restore speed. However, it is practically to find a solution that performs the best in all metrics. So we aim to find a solution with the following properties. It must have certain high backup performance as the top priority, and it performs the reasonable trade-offs in the remaining metrics. This two figure compares the exact duplication, two kinds of exact duplication in terms of lookup overheads and update overheads. In the left figure, the red line shows the ever-increasing lookup overheads in physical locality because of the fragmentation problem. On the contrary, the logical locality have a much certain low lookup overhead. And the right figure shows however, the logical locality have a significantly higher update overhead than the physical locality, but the sampling optimization is very efficient to reduce the update overhead without increasing the lookup overhead. These two figures compares the new exact duplication, two kinds of new exact duplication in terms of deduplication ratio. They explore is either physical locality and or logical locality, and in the our observation is that in the kernel and RDB datasets, the logical locality achieves a better deduplication ratio than physical locality. However, in the VMDK dataset, the physical locality achieves a better deduplication ratio than logical locality. This is because self-references are very common in VMDK dataset. So we recommend a more complicated workflow in VMDK dataset to explore the logical locality, namely the similarity detection approach. This two figure shows the interplays between fingerprint index and the rewriting algorithm. In the left figure, the red line shows ever increasing lookup overheads in physical locality, and but with the help of a rewriting algorithm, HAR, the blue line achieves a more certain and a lower lookup overhead. It is because the rewriting algorithm reduced the fragmentation. And in the right figure, we examine how does the fingerprint index affect the rewriting algorithm. We examine the deduplication ratio of rewriting algorithms under the 4 kinds of fingerprint indexes, and we find that the exact duplication exploiting physical locality achieves the highest duplication ratio in all of these data sets. So our conclusion is that exact duplication exploiting physical locality has the best interplays with the rewriting algorithm. This figure explores the interplays between rewriting and restoring algorithm. The y-axis shows the restore speed. Without the rewriting algorithm HAR, we've observed that the assembly area, the forward assembly area technique achieves the best restore performance, but with an efficient rewriting algorithm HAR, the Belady's optimal replacement cache achieves the best restore performance. We don't show all of our experimental results in this talk, and you can find more results and findings in our paper. And so let's conclude our paper. In our paper, we first proposed a taxonomy to understand the parameter space of data duplication, and then we design and implement a framework to evaluate the parameter space. And other researchers also can implement their new ideas in the framework for evaluation. It enables apple-to-apple comparisons between existing solutions and potential solutions. And finally, we present our experimental results and draw the following recommendations. Because, as mentioned previously, no single solutions can perform best in all metrics, so we recommend different solutions according to users' demand. For example, if we need the lowest storage cost and the highest duplication ratio, we recommend the exact duplication exploring the logical locality with the container-defined segmenting and the random sampling configurations. If we need the lowest memory footprint, we recommend the new exact duplication, and we explore its physical locality for its simplest logical frame, and explore its logical locality for its relatively higher duplication ratio. And if we need a certain high restore performance, we recommend exact duplication exploring the physical locality because it has best interplays with the rewriting algorithm. Thank you for your attention, and I would like to take your questions. Thank you.
Mark Lillibridge, HP Labs. I actually have 2 comments rather than questions. First, I think the data sets you're using are not sufficient to actually evaluate fragmentation properly. In the real world, when, for example, you're combining backups of thousands of machines, there's a lot of similarity across machines. And so simple rewriting algorithms that assume that, well, if the backup looked like this yesterday, it'll look roughly the same tomorrow, don't actually work because there's so much similarity across machines. So I would take a lot of the results involving rewriting and fragmentation in your work with a truckload of salt. Second, it is true that if you keep parameters like the chunking size the same, that the conclusions about storage cost you list in memory fingerprint are correct. But that's not what people do in practice, right? You have parameters like the chunking size you can change. And so I could choose a small memory fingerprint, or I could make a bigger memory fingerprint and improve my dedupe ratio. And so I think some of the conclusions there, if you actually allow fully varying things, don't follow either.
Okay, thanks. Regarding the first question, our data sets are commonly used in previous work. The first kernel. Okay. Regarding the second question, you can in the evaluation we use the same chunk size in all these data sets and to evaluate all solutions. You claim you can decrease the chunk size, but in some kinds of fingerprint indexes, but reducing the chunk size. Also, reducing chunk size potentially can improve the deduplication ratio, but it increases the overhead of the recipe. It's a trade-off.
I'm not claiming.
All right, take it offline. Yeah. And I'm afraid we don't have time for another question. We ran over. So let's thank the speaker again.
Thank you.